Okay. Does this work? Oh, it does work. That's cool. Okay, thanks everybody. Welcome to the session tonight. I'm going to talk about the main types of telescope we use as amateurs, largely in three main categories. I want this to be interactive though, so I've got a bunch of stuff. I'm going to talk about the history, I'm going to talk about what we use them for, some of the positives and negatives, but I'm happy to go off on a tangent and ask questions and have a little bit of a discussion about it. And if I don't know the answer, probably Bill does, or one of us do here. So I'm going to kind of walk along a timeline. Going to talk about what are the things, what are the different aspects of the different telescope designs. What does it mean for us as astronomers? Start off with quick show of hands. How many here have got binoculars? Yeah, good. Everybody should have binoculars. How many here have got Dobsonians? How many have got refractors? How many have got Schmidt-Cassegrains? Okay, cool. Yeah. How many have got ones that I haven't talked about? Yeah? What do you got? Smart telescope. Smart telescope. Okay, generally a Newtonian, but with the imager instead of the secondary. Who else has got something different? Dal Kirkham, nice. Yeah. Who else? Anybody else? Was another hand somewhere? Max. You got a Mac. Oh, cool, awesome. Right, so pretty much all of those fit into these three types, right? So a refractor, which uses lenses, a reflector that uses mirrors, and a catadiatropic, which is a mixture of both, right? So all of those fit in there. So your Macs are a cat, the Dal Kirkham's a reflector, and everything else is somewhere in between. So telescopes. The word telescope was coined in 1611 by Greek mathematician Giovanni, and I'm going to screw this up, Domitiani. And he saw Galileo's telescope, and he basically came up with the name that means far-seeing. And that actually, that far-seeing is really important. It means a telescope's really for us to see things that are too faint or too far away for our eyes. When we get into astronomy, oftentimes we think about a telescope as being something that makes things bigger. And making things bigger and magnifying is part of it, but actually it's more about capturing more light. So this is kind of I don't think my laser pointer thing is going to work, but this is kind of a view of a basic telescope. And what it does is uses a lens. In this case, this is a refractor. Uses a lens to take to get an image of a distant object. It creates a real image of that object within the telescope, and we use an eyepiece to view that real image, to create a virtual image, which looks bigger. Because bigger things are closer to us, we perceive that as being closer. But the most important thing is actually the aperture. That magnification, we can change that magnification by changing that eyepiece at number 2 there, or we can choose any magnification. But the real important thing is the aperture at number 1 allows us to gather more light. So even a relatively small, so your dark adapted pupil is probably 7 millimeters in your eye, and you get a relatively small telescope, maybe 70 millimeters. And that's capturing about 100 times more light than your eye can. So the important thing about a telescope is not that it makes things bigger, it's that it makes things more visible. It means it takes things that are too far away for us to perceive, too far away for us to resolve with our eyes, and makes it easy to resolve. You can think of a telescope as being a bigger eye, or a bigger pupil for your eye, and that's super important. Where's my maps? There it is. Really, all of the telescopes that we're going to talk about are just a different way of getting more light into our eye. They're all doing the same job in slightly different ways. So, talking about refractors, possibly the simplest style of telescope. So the brass telescope there is a refractor. Originally, built by a Dutch-German spectacle maker. So a German guy moved to the Netherlands called Hans Lippershey. He was the first to apply for a patent, and he called it his Dutch perspective glasses. He said that he used that phrase for seeing things that are far away as if they were nearby. Ultimately, his patent, though, was rejected because at the time, a lot of spectacle makers were doing the same thing, holding up different lenses and working out the same thing, that you could make something that's far away appear closer. But he did make and sell his early telescopes. One of those telescopes made its way to Galileo. And so in 1610, he improved on the design. He ultimately ended up with a 3 times magnification, and then eventually up to 30 times magnification. But he was the first really to point the telescope at the sky to make a difference and observe what he could see. Notably, he discovered the 4 largest moons of Jupiter, which led into big discussions in terms of how the universe is structured, not the topic of this lecture. He also observed Saturn, which he thought had 2 small planets next to it. He saw these sort of ears on Saturn, and he thought they were 2 small planets. And then a number of years later, he looked again, and he couldn't see them at all, and he thought they'd disappeared. And what had actually happened with Saturn is as it is now, the rings were edge-on, but his early telescope couldn't resolve those edge-on rings. The biggest problem with early refractors was chromatic aberration. So lenses, when they focus light, the different colors of light, the different wavelengths, don't all focus at the same point. So blue focuses a little bit closer to the lens, red focuses a little bit further away. What this means is looking at stars, you see color fringes. And this was a feature of all early telescopes, all early refractors. So by 1729, a lawyer called Chester Moore Hall actually worked out that, well, he was thinking about the problem, and he was thinking about how eyes have got different types of material in them, and he started to experiment with different types of glass. He worked out that if he used crown and flint glass, that he could correct for much of the aberration. He wanted to make a telescope for himself. His interests weren't actually to make loads of money out of this. He wanted a telescope. So he ordered 2 lenses from different opticians to be able to create his telescope. One made of crown glass from one optician, and one made of flint glass from another optician. These 2 opticians, though, they didn't really do all of their own lens grinding, and they both outsourced this job to another lens maker who actually got both of the orders. He worked out that these lenses were, these are the same size, they're going to the same customer, what's going on here? That was George Bass. He was a lens maker. He eventually shared this with John Dolland. There is a great talk about John Dolland on our YouTube channel, incidentally. It's a few years ago, but a really good talk about John Dolland. Anyway, he takes this and he runs with it. So John Dolland publishes a paper. He does a lot of investigation work, and he publishes a scientific paper about how these the combination of these lenses makes a really good imaging system. And then he goes on to patent this. So in, what was it? Oh, it's probably on here. 1758, he publishes, he was granted a patent for this mixture of crown and flint glass, which work to the 2 different types of glass refract the light slightly differently, bring it to a closer focus. Not perfect, though. Now, John's son, Peter, actually, a little later, invents the apochromat, where he takes 3 different types of glass, or it may be more, using some exotic types of glass to correct that even more. And that's sort of where we get to in the modern era. We've not really taken many leaps other than improving on the apochromat to take really sharp images where all the colors come to the same focus. So they end up, these 2 are both, so the achromat and apochromat are both still around with us today. Typically the achromats are the cheaper more accessible telescopes, and the APOs are the more expensive. In general, refractors, they give a really good, sharp image. There's nothing to interfere with that image. They're highly prized by astrophotographers, particularly the apochromatics, and they work really, really well. However, glass is heavy, particularly when you've got a lot of elements, and it's expensive, and it's very expensive to make big. So we have a bit of a trade-off. So refractors don't really get to really large sizes. Any of you got any comments on refractors or any questions about refractors before we move on to the next class?
Yeah, just you're talking about the cost. Until fairly recently, apochromats were pretty much beyond the budget of most amateurs, but that kind of has changed because although they're still more expensive, the difference isn't as great as it used to be.
No, that's right. So with a lot of particularly manufacturers in China, some of them creatively using the designs of other companies, they've become a lot more affordable. And just with technology moving on and ease of manufacture. So yeah, you can get APOs pretty affordably, but they're still small aperture. And as I said, the kind of key feature of why we use a telescope is to gather more light. So what you tend to see is even expensive refractor telescopes probably don't generally have an aperture much more than this telescope, right? So this is an SCT we'll talk about later. But you don't really get huge telescopes. And why does that not really matter? Because a lot of people who are buying the scopes that Bill's talking about are using them for astrophotography. So with astrophotography, we can gather more light just by taking more images or exposing for longer. So that's really opened up the world of astrophotography. Reflectors. So pretty much as soon as the refracting telescope was popularized, people were experimenting and playing with curved mirrors to do the same thing. The knowledge that a curved mirror would focus light had been around for probably 400 years at that point. So it wasn't a surprise that, that curved mirrors could be used for this. So there were a couple of notable people who were doing work on this, Giovanni Sagrado, Niccolo Zucchi. But the problem that they had was making a mirror, making a reflective surface accurately enough to focus light in a way that you could get an image from it was actually really difficult. 1668, Isaac Newton took on this challenge. He ground a mirror, a spherical mirror, out of specular metal, which is alloy of tin and copper. He built something like this. This is a reproduction of what his telescope would have been. And he used that to look at the stars. Notably, the advantage of using a mirror is we talked about the chromatic aberration. Well, that's not present in a mirror because a mirror reflects all wavelengths of light equally. So you'll remember from your high school science class that angle of incidence equals angle of reflection. So all the light comes off at the same angle. So this allowed you to make a telescope that didn't have any chromatic aberration, and at this point in Newton's time, they didn't have the capability to make the achromats and apochromats. 1780s, William Herschel built his own tools to grind bigger and bigger and bigger mirrors. If anyone's ever been to the Science Museum in London, there's some really cool displays of Herschel's tools there, some of Herschel's telescopes. And he was still using specular metal to do this, but he perfected a way of grinding this specular metal into a really nice figured surface so that he could use bigger and bigger apertures to get more and more detailed views of the skies. Specular metal, though, was hard to work with, it was heavy, and most importantly, it tarnished. So you leave it open to the atmosphere, and as you do with a reflector telescope, there's nothing holding it in. it needs to be cleaned, repolished, and it changes the figure. So really hard to work with. In the 1850s, French physicist Léon Foucault came up with a way to use silvered glass as a mirror. So taking a figured piece of glass and silvering that to reflect light. He also invented a way to check the figure of that mirror by using a knife edge. So viewing a pinpoint light across a knife edge allowed you to get the viewer sees a pattern on the glass of how essentially it magnifies any imperfections. So you could look along this knife edge and you can see if there's imperfections on the glass when illuminated by this point source. So he was able to create very, very accurately ground glass mirrors, and glass was able to be made much bigger, much easier, and ground much easier, and then silvered. Ultimately, that led to bigger and bigger telescopes. By 1917, we had a 100-inch telescope, the 100-inch Hooker telescope at Mount Wilson. That was the one that Edwin Hubble used to make his discoveries about the expansion of the universe. And then 200-inch telescopes like the Hale telescope at Palomar. And then ultimately, this same technique is where we still are in terms of making a first surface silvered mirror to make telescopes like the 10-meter Keck telescope. We've improved the techniques such as making segmented mirrors, being able to change the orientation and shape of the figure of the mirrors to counteract the atmospheric distortion. But ultimately, it's the same thing. For us astronomers, what are the advantages, disadvantages of, for amateur astronomers, what are the advantages, disadvantages of reflector telescopes? So most of you are familiar with the Dobsonian telescope. That's a reflector telescope. It's a tube with a mirror in the bottom. It is face silvered. That means that the glass blank, which is the reflecting surface, is figured. It's turned into, in this case, it's a parabolic curve. And then it is silvered. So metal is put on the top of it, essentially. And that's the reflective surface. So the light does not go through any glass. It goes straight to the silvered surface. That means you don't get any stray reflections and you don't get any issues with refraction. There are some negatives to the sort of basic reflector type telescope. In the Newtonian type, where we got a secondary mirror, so the way that this works, I probably should have pointed that out on top. Light comes in at the end, hits the mirror, reflects off to a secondary mirror, so that's a flat mirror. So a parabolic mirror on the end, the yellow one. The light reflects off a flat mirror, which is the secondary, and into the eyepiece. That secondary mirror has to be held up, so that it's held up by usually these little metal vanes. So a thin piece of metal holds it into the middle. Light passes around those vanes and it diffracts, so you end up with diffraction spikes. That's why bright stars in an image through a Newtonian telescope like this will have spikes on it. You can actually tell how the secondary is held in by how many spikes there are. If you were to put 3 vanes on the spider, you'd end up with 6 spikes. If you look at images online from the James Webb telescope versus images online from the Hubble telescope, you'll see that there are a different number of spikes on there, all to do with how the secondary mirror is held up. The other issue with these Newtonian type reflector telescopes is coma. So whilst a parabolic mirror that we use in here is good at focusing light quite cleanly, and there is no chromatic aberration, particularly at the edges of the field, the light gets a little bit stretched and stars might look like they've got little comet tails, hence why we call it coma. So a parabolic reflector has issues with coma. Now you can get a coma corrector, which is another piece of glass that you put in the eyepiece that will attempt to solve and resolve some of those coma issues. But you're adding more things into that. So obviously, the more glass you add into the eyepiece, you're also ending up with potentially chromatic aberration, which is what you sought to get rid of by using a mirror in the first place. That said, you can get bigger and bigger apertures of a reflector telescope for not the same sort of money or not the same sort of complexity and weight as you would with other types. And collimation. So a reflector telescope is more sensitive to collimation. So what is collimation? Probably most of you know this, but collimation is where we align the two mirrors so that the light is passing directly down the tube, directly back to the secondary and directly into the eyepiece. If those mirrors are misaligned even a fraction, the stars appear to be blown out in one direction. So these images here, that's an image of a star that's been unfocused. And this is what you want. This is a collimated telescope. The one on the side, you can see it sort of squished to one side. That's an uncollimated telescope. So Newtonian reflectors particularly are quite sensitive to collimation. So if you're picking them up, throwing them in the car, taking them out somewhere to observe, you become very familiar very quick with how to do a collimation. So that is kind of a bit of a disadvantage of that sort of telescope. Sorry, did somebody have a question then? No. I guess the only other thing that's kind of a bit of a challenge compared to refractors is because you have an open tube design, so you've got a tube with a big open part to let the light into the mirror. That also lets dust in here and spiders and mice and stray screwdrivers from when you're doing your collimation and all of the things. So that can be kind of a disadvantage. Any war stories for reflectors or bad or nightmares collimating or? No, okay.
Is G a problem for refractors? Because you said a problem with
For refractors?
Yeah, well, I mean, it is a problem for refractors. Do you have the same problem?
So refractors, it's definitely a problem because you've got a glass surface right at the end of the tube, so any dew will settle on there. For reflectors, like a Newtonian reflector, less susceptible, but not completely non-susceptible. So really, anything that's exposed to the air can be dewed. It is less likely that down the end of the tube you're going to have problems with dewing. But absolutely using, anybody who's used a Dob for any length of time in Auckland knows that when we get into the humid summer, it is perfectly possible for the secondary mirror to fog up with dew. What can you do? Really the same sort of things that you do with other classes of other types of telescope. You can use a dew shield. Most refractors that you buy commercially come with a dew shield. Usually it slides up, and that dew shield is really just the tube that extends over the end. You can make that with a piece of cardboard or a piece of foam. Yoga mats work really good for making dew shields, actually. And the same with a reflector, the same with the Dobsoni. If you find that it's super humid and you're getting dewing on the secondary mirror, you can actually just wrap a bit of cardboard and extend out a little bit. More likely if you're looking quite high up. But yeah, it's a good question, and it does happen for reflector types. Some other reflector types, a Gregorian reflector. Now this was designed by a Scottish guy called James Gregory. He actually designed this before Newton designed his telescope. He predated Newton designing a reflector, but he never made it. He didn't build it, and it wasn't built, and Newton made his reflector, and that sort of became popular. Then about 5 years later, somebody built a Gregorian reflector. I forgot the name, and I don't think I've got it written down who it was that built it, unfortunately. It was 5 years later it was built. It gave an upright image, which was interesting at the time because people weren't really thinking about that. People were using telescopes to look out into the distance terrestrially, not just at the stars. So an upright image actually was quite a feature. It actually has two concave mirrors, which is a little unusual. Next sort of type of reflector that we'll talk about is a classic cassegrain. So very similar to the Gregorian reflector actually, but it has a parabolic primary mirror, same as the Newtonian reflector does, but a hyperbolic secondary, so a more complicated figure on the secondary. With both of these, the light comes in at the end. The light's reflected from the primary mirror into the secondary mirror and then out of a hole through the primary mirror out of the back. The Zeiss telescope is a classic cassegrain, so it has the same figure as that. It has the parabolic primary, hyperbolic secondary. If you switch that primary to be a hyperbolic figure on the mirror, And why would you do that? To improve these aberrations, so get rid of coma, particularly. You end up with a Ritchie-Creation. Now, the Ritchie-Creation design, 2 hyperbolic mirrors, same layout, same structure as the Zeiss, but with different figured mirrors. That's the basis of most professional telescopes today. So most observatories have an RC design. The Hubble Space Telescope is an RC design. And you guys know the story of the Hubble Space Telescope? Yeah, so they launched... so the thing about Ritchie-Creation designs, this hyperbolic figure is really, really important. Getting the shape right on these mirrors, super important. Getting the distance correct between the mirrors is as well. So there are tools that you can build to get the figure, and when the Hubble Space Telescope was being built, they built these tools. They built them very expensively, as anything that goes into space does, but they couldn't test this on Earth, so they put a lot of effort into the tools to figure the mirrors. They launched the Hubble Space Telescope, and they took images, and the images were terrible. There was a huge investigation, there was a huge load of controversy about that, but long story short, the mirrors hadn't been figured correctly. They found that there was a fault in the tool that they'd used it, so the measurements were all slightly off. But they had built this tool amazingly well. So whilst there was a fault on the primary mirror of the Hubble Space Telescope, it was a perfect fault. The mirror was perfectly figured wrongly. A little bit of clever thinking later allowed the scientists to come up with a corrector. Basically a part of the optical chain that would invert the error that was caused by this incorrectly figured mirror. They were able to install that whilst the space telescope was still in space, and every great image you've seen from Hubble has been post that fix. So I should have given you an image of this, but there are images. If you just search Hubble controversy or Hubble corrector, you'll find images of what they look like when they got first light from Hubble, and it was pretty terrible.
A question: you lose a lot of light actually on the design, I guess, or not?
Yeah. So I mean, with all of the reflectors, where you've got a secondary in the middle of the optical path, you are losing light. So absolutely, you are. And in fact, for the Ritchie-Creation design, the size of the secondary mirror is actually much bigger in relation to the overall aperture. So classic Cassegrain, if you look at the Zeiss, to start off with a Newtonian reflector, you don't really, particularly because it's a flat mirror on the secondary, you don't really need to take up that much space of the overall aperture. If you go and look at the Zeiss, there's which is a classic Cassegrain. The secondary takes up a reasonable chunk of the center of that. So the Zeiss has a 500mm mirror, the hole in the middle of the mirror, which obviously doesn't reflect any light, it's probably about that big. So you are losing light on that. But because it's relatively easy to scale up a mirror versus scaling up a lens, it's not that hard to make your mirror a little bit bigger to capture more light. The hole doesn't cause a problem. You don't lose any... you don't get images with holes in the middle or anything. It's because everything's focused to the same point. It doesn't really cause a problem, but absolutely it does take some light away from your image. Interesting what we do on the Zeiss when we're particularly looking at the moon. What we often do is close one of the shutters on the Zeiss, so we're actually using half of the mirror. And what that does is you still get a sharp image, but you lose a good chunk of the brightness. So yeah, that was a good question.
It does cause a small loss of contrast as well.
You're getting refraction. Yeah, absolutely. Doesn't matter too much on the moon, which has got a lot of contrast anyway. But yeah, you do, absolutely. Anything that you put in the light path is going to cause a diffraction. So the great thing about a RC is you don't get any coma. You don't get any third order coma. You do get some fifth order coma. and you don't get any spherical aberration that you might from other designs. Unless the mirror spacing is wrong. So something with an RC that we learned to our peril when we put an RC in at Kumiu is that the distance between there and there is supercritical. If you don't get that right, you start to see a spherical aberration in the images. So we didn't know that before we did that, and we learned that pretty quick. And it's kind of funky to try and space that. We had the specs from the factory that told us exactly what the distance from that part of the secondary to there was, the hole in the middle of the mirror. That wasn't very useful, unfortunately. So we had to, there was a lot of trial and error to get that somewhere near when we were trying to do that. And then sort of I'm not going to say the last type because there are others, but the other variant of the same one is the Dol-Kirkham. So the Dol-Kirkham has an elliptical primary and a spherical, spelt wrong, the secondary, which means it's less complicated to produce, for one. It is easy to get better figured elliptical and spherical mirrors than it is to get hyperbolic mirrors. They're a little bit less sensitive to some of those things like the spacing. But as Bill was saying before, do you want to give your spiel? Because Bill is our resident Dol-Kirkham lover on the council.
Quite a lot of the commercial ones are now sold as corrected Dol-Kirkhams because the basic Dol-Kirkham design is great for central of field things like if you're looking at planets, so the aberrations are well controlled there, but you get to the outer part of the field, you start to get noticeable aberrations, so they're not very good for imaging because you'll notice that things start getting smeared out in the corners of your images, especially if you've got a camera with a large sensor. So what they do is they put in a sub-aperture corrector which basically fixes the aberrations, and they've got it pretty pat now. The corrected Dol-Kirkhams are often used for astrophotography, and they do really well. Well, one thing I was going to mention about with these reflectors, they all have to have some way of holding the secondary mirror, as you mentioned, Steve. And this actually, the refractor people actually copied that and deliberately put wires across the front of their lenses so they can get diffraction spikes in their images because people think they look cool.
Yeah, we're so used to seeing diffraction spikes. In fact, that's a Hubble image there, and you can see there's diffraction spikes on there. So we're so used to that, and it looks cool that yeah, a lot of people on refractors think, I wish I had refraction spikes. But yeah, you can get two pieces of wire and put them over your lens at the top, and yeah, you can have your own diffraction spikes. There's some interesting articles online about testing different ways of holding a secondary, having a single, you can do it with a single rod, and you can have two, you can have three, you can have four, and what it does to the image. So if I find that, I'll put that up on the note on this video on YouTube. I'll put them in the comments there, link to that. There are some other variants of reflectors. One that you might come across in cheaper telescopes, entry-level ones, is a variant of the Newtonian reflector, where they tend to sell them as short tube, or they may well be sort of 1 or 2 meter focal length, and the length of the tube is significantly smaller than that. And that's a Jones-Bird or Bird-Jones design, often used on cheap telescopes. But the design itself isn't actually bad. So that design uses a spherical mirror in a Newtonian like this, but also has a corrector, which is essentially in the eyepiece that will correct for the spherical aberrations. One of the features of that design is that corrector will tend to magnify the image. So you would get a shorter tube or a longer focal length for the same size tube reflector. Unfortunately, because commerce is what it is, that design has kind of been taken over by usually all the entry-level Newtonians, and they use a spherical mirror because a spherical mirror is cheap to produce, a lot cheaper than a parabolic mirror. But instead of having a proper corrector, they effectively just have a Barlow lens. They effectively just have a magnifying lens. So it doesn't really correct for the spherical aberration. What it does is just magnify the center of the image where the spherical aberration isn't quite as bad. So a lot of the kind of 4 and 5 inch Newtonian reflectors that are quite small on a tripod will be that Jones Bird design, but kind of a cheaped out version of it. So you might see that. So if you ever take apart one of those telescopes, you'll realize that if you look in the eyepiece hole, you'll realize that it's not just a hole. So this, I can put my fingers in there and I can touch my fingers. On a Bird Jones design, there's a piece of glass in there, and then you've just put a fingerprint on that if you tried that. So don't do that and say that I told you, because yeah, that's not a good idea. Anything else on reflectors? Any bits I've missed? Any bits of wisdom that everybody always wanted to know? Any horror stories again? No, okay. So the last class is catadioptrics. So that kind of means lenses and mirrors. This is a hybrid of what happens when you use both a lens and a mirror. Why do we want to do that? Well, for the same sort of reason as I just explained that Bird Jones design. You could argue that that is a catadioptric design. It's about removing those aberrations from using easy to figure lenses effectively. So a spherical lens is easy to figure, but it's got aberrations. It's got the light doesn't focus quite cleanly. So first developed in 1930 by Bernhard Schmidt. He created the Schmidt camera, and essentially it uses a spherical mirror with which is what has become known as Schmidt corrector plate. And really that's a special kind of lens, a very weak lens with a particular figure on it. That's what a Schmidt corrector plate looks like in the figure. That's super, super exaggerated. To look at a corrector plate, and there's one on here. So this is a corrector plate, which I will just move that because I can't override. So on there is a piece of glass. That piece of glass is not just a piece of glass, it's actually a very weak lens. What that does is, yeah, as I said, it corrects the figure from using a spherical mirror. Used for quite big telescopes, but because of the size of this piece of glass, this huge lens, it's a very, as I say, it doesn't have to be very thick compared to the size of the telescope. It was used to make observatory class telescopes. They were big and bulky, but hard to make, expensive. They didn't really take off for amateur astronomy. In 1940, Dmitry Maksutov, so was somebody who has a Mac that I said at the start, that developed another kind of catadioptric telescope, and this one used a simplified version. Instead of a very complicated figured corrector plate, it was a smooth, spherical, curved meniscus lens. So the whole thing is the same thickness all the way through, and it's curved. And the really cool part about the design is that the design of the secondary spot, so the secondary reflector, the curvature that's needed is exactly the same curvature as is needed for the corrector plate. So it allows you to make a single piece of glass, illuminize a spot onto the middle, and that's it. You're good to go. You don't need a second mirror. Because everything's spherical, it doesn't really need to be collimated to be changed because it's sort of the same figure. Even if you tilt it, it just needs to be aligned, really. Maksutov's very popular for planetary, so you get really good for long focal length observing. But the corrector plate is pretty heavy. So usually most Macs you see are about this sort of size, maybe just a little bit bigger in the amateur market. But a very good scope and yeah, provide some really sharp images, particularly high magnification planetary images.
Well, Steve just mentioned the society actually owned a 12-inch Maksutov, which was bequeathed to the society.
Yes.
Unfortunately, it's never really been used because it's enormously heavy and it's not, it really would need an observatory to house it in such a large telescope.
And an incredibly chunky mount to mount it on. So yeah, if anybody does ever want a project to resurrect a 12-inch Maksutov, come and see us. We would be very, very interested in hooking you up with some really, actually, I mean, I've never looked at it. It was out of commission long before I joined the society, but reportedly it was a very good scope. Yeah. So, and in 1970, Tom Johnson, who's the founder of Celestron, came up with a really smart way of mass manufacturing these corrector plates. He came up with a mass factory-based process whereby he could churn these out in the bucket load. And so from the 70s and 80s, particularly with Celestrons, this is one of the early adverts. So most people here look like they're younger than me, so might not recognize Spock from Star Trek. Yeah. So that's Spock from Star Trek. When I explore the real universe, I use precision optics from Celestron. And really it was a game changer for amateur astronomy, because the SCT telescope, so Schmidt-Cassegrain telescope, a Cassegrain design with a mirror at the back and the light coming in the front, and then bouncing off a secondary and coming through the back, the Schmidt-Cassegrain really became very popular for amateurs because for a number of reasons. One, it's a very compact design, because just like all of the Cassegrains, the light path is folded. It comes in and goes out and goes back again. For the focal length, it's a very short telescope. They can be made to really quite useful apertures without making them too unwieldy and too heavy. The C8 was actually the first Schmidt-Cassegrain telescope. So C8 is 8-inch Celestron. So we have one of those. I was going to set that one up, but didn't quite have time. We've got one that looks just like that. They became iconic, the orange tube C8. Easy for one person to pick up, throw on the tripod, do some observing, and then put away. But they're also quite beneficial because the corrector plate on the front seals the tube from dust getting in there. So you have less problems with having to clean your optics. They are easy to collimate. They keep their collimation really, really well. Part of that is that the mirror is spherical, so you don't need to adjust the primary mirror at all. On a Newtonian, you've got to adjust the primary and the secondary. And because the secondary is also spherical, you really only need to adjust that to make sure that that is lined up to send the light back down. Very easy to collimate, although you can't use the same collimation tools as you might for a Newtonian. But really became super, super, super popular. But I guess some of the areas where it wasn't is because they do tend to have longer focal lengths, not quite as useful for wide field. So a lot of astrophotographers still use Newtonians because you can get a fast wide field Newtonian, where it's hard to get a wide field fast Schmidt-Cassegrain. And more expensive. So bang for buck or dollars for photons. You can capture more photons, you can capture a bigger aperture for your dollars with a Newtonian. You might be able to get a 12-inch Dob for the same price as an 8-inch Schmidt-Cassegrain or even smaller. So really sort of that sort of price point. Questions on Schmidt-Cassegrains or?
In general, if you get some dirt or dust, how do you clean, and what do you use to clean?
So on the corrector plate, that's a cue. Yeah. So I have a whole talk on cleaning, but so you'll find it on the YouTube, and I'm sure I'll do it again soon. But it's not as scary as it sounds. With any telescope and any optical equipment, my first thing is, do you really need to clean it? And if your answer is I don't know, you probably don't need to clean it and don't need to worry about it. Cleaning any optical surface, you've got to be very, very careful, because it's not that you're going to damage the glass. You definitely won't damage the glass unless you're cleaning it with a chisel. But it's about, particularly on modern scopes, and the same with glasses, right? So my glasses have got anti-reflective coatings. The optician cons you into spending an extra $300 or whatever to have all the fancy coatings on. And yeah, then I still go and clean it with a t-shirt and then regret it, right? So second pair of glasses, my old one is scratched, but my other pair is scratched, and I didn't really learn that lesson. But with your telescope, where you pay probably more than your glasses, yeah, absolutely. Those coatings on there are quite fragile. It takes just a piece of grit that's got blown up onto the lens, maybe it's stuck there on a fingerprint, to damage that anti-reflective coating. What does that damage do? It's not really going to stop light, But what it will do, and as Bill was saying before, when you close the door on the Zeiss, you lose contrast because you're getting diffraction. Those scratches on the optics cause their own diffraction patterns. And what you wouldn't notice that as a diffraction spike, like you might if you put a wire on there. Maybe you wouldn't, depends how big your scratch is. But you would notice that you're losing contrast. And contrast is what you need to be able to see these faint fuzzies in the sky. You want to be able to separate the little gray blob from the black background. So cleaning-wise, it's not that hard. So I use a cleaning solution, which is 30% isopropyl alcohol, 70% demineralized water, and a couple of drops max of dishwashing detergent to every sort of 300 ml. So 1 or 2 for every sort of 300 ml. I make it up in a spray bottle. Don't ever spray onto the telescope itself. Spray bottle is just convenient. Spray onto a lint-free, non-scratch cloth. It could be even a tissue, which tissues can make a mess, but a clean white tissue, non-recycled and non-coated, nothing with aloe vera on. They work pretty well. Or you can use things like Kim wipes. If you've ever heard of Kim wipes, they're kind of what the industry uses as wipes. They're quite good. Gently sort of clean with maybe a dabbing motion at first to pick up any of that, any grit. So I have a damp cloth. I'll sort of dab it around until I know I've got all of the grit and residue. Actually, first blow it off with a bulb blower. Not Candair, don't use Candair. And then as you clean it, you can be a little bit more, put a little bit more pressure on there. So yes, not too difficult to clean. If you're going hardcore, you might disassemble it and wash it in the sink. Certainly that's the way of doing it. Actually washing telescope mirrors in the sink with some running water and detergent and using your fingers is actually a really good way of doing that, as long as it's wet the whole time, stays submerged. So that's certainly, you can do that. You just got to be careful of scratches. Really, scratches is your enemy on cleaning anything. And if you're not sure, don't do it. But yeah, there's a whole talk. There's probably 2 versions of it on YouTube, and I'm sure I'll do it again in the next few months. So good question. Any other questions on there? Okay, so sort of wrap up in terms of what are the types and what might we choose if we're looking to buy a telescope. The refractor, kind of sharp image, simple to use. Clean images, great for photography, great for planets, great for wide field. You can get really fast refractors. Cheap ones are not so great though. You get a lot of this chromatic aberration. You get the fringes, purple, green fringes when you're looking at bright objects. Same with cheap binoculars. To get the really good ones, you got to spend a lot of money, many thousands of dollars. So, it's a Skywatcher 100 mil Esprit, probably costs, so that's 100 mil aperture, probably costs about maybe 3 times what that 8-inch Dob does. So, and you still got to buy a mount to put it on. So really more expensive to get the good quality refractors. Reflectors, you'll have heard the term light buckets, maximum aperture, collect as much light as possible. Really good bang for buck, dollars for photons. Easy to use, quite simple, but with the negatives and drawbacks of having to deal with coma, maybe a coma corrector, having to deal with collimation, maybe a bit longer and harder to use. But certainly easy to use, easy to get a lot of light. And then sort of the cats, which are really the all-rounder. They're sort of a combination of the both. They sit sort of in the middle. A little bit more expensive than having a Newtonian. They're often paired with go-to mounts as packages. We've lost Meade as a manufacturer, so it's kind of Celestron who are kind of the main in the field now. But generally really good coatings on the optics, really good images, easy to collimate. And that's basically the 3 types, the 3 categories that are in there and how we use them. So I guess with that, any questions?
Just with the antique kind of telescope I've looked through, when you're looking through it, like on Earth, the the images are upside down.
Mm-hmm.
What's missing?
What's missing? Well, there's nothing necessarily missing. If it's an astronomical telescope, most astronomical telescopes have an upside down image. Why? Well, actually, you can get away with less glass. And you don't need the image to be the right way up when you're looking up. So if you've got this Newtonian here, not only is this image not the right way up, but because the eyepiece is at the side and on an angle, it's twisted too. So if you look through this, actually, it's your image will be at a nice jaunty angle. But it doesn't matter when you're looking up in the sky. And it really doesn't matter when you realize that as things move across the sky, they're rotating as well. So when you're looking at it one part of the sky, it's in a different orientation. So it is possible for any telescope to get what's called an erecting eyepiece, which has got an extra lens element in there, which essentially inverts the image. So you can get an erecting eyepiece and put it in a Newtonian, point it down and look out to sea and watch the boats go by. So you can certainly do that. Might still be tilted on there, but
binoculars usually do that with a prism, so
yeah.
because they're used for terrestrial use a lot, you want the image to be the right way up, so they use a prism to create the... That's
right. So binoculars use one of two types of prism: a poro prism, which is kind of a pentagonal shape, or a roof prism, which is another shape. Generally, the binoculars with a big bulge on the middle are a poro prism, and their light path in that is slightly cleaner, so they're better for astronomy. A roof prism binoculars, the ones that look more like an H, so often like the spotting scopes, they're like a really flat H. They're not quite as good for astronomy. So if you're choosing binoculars for astronomy, probably choose a poro prism one. So I used to be one of the directors of Astrons. Niven is now one of the directors. He's the chair of Astrons. When we first started selling binoculars, we did a lot of research on what do we ask the manufacturer to have in our binoculars, and having fully multi-coated lenses and a poro prism, and we tried at 8 times and 10 times binoculars, and we landed on the 10 with the poro prisms and the fully multi-coated. But it does make a difference. It just and the coatings themselves, actually, I never said what the coatings do. The coatings increase contrast. So if you scratch them and reduce your contrast, you're negating all the benefits you get from it. So yes, it is possible to have a telescope. I'm going off on a tangent, but it is possible to have a telescope that has a correct right side up image.
Just on that, Galileo's telescope actually gave an image the right way up, and that is because it had a negative eyepiece lens. But Kepler came up with the idea of using two positive lenses, but that inverts the image. But for astronomy, it didn't matter, and you got a better field of view. Yeah,
I didn't talk about that. So a Keplerian refractor is a different lens design. So as Phil says, use an inverse lens to flip the image.
On that point, I've only really noticed people bothered by that. They're looking at something on the ground.
Great.
So sometimes when we do outreach and it's a bit cloudy, or look at the sky tower or something like that, and it's upside down. The other thing is when they're looking at the moon, because they can see the moon, and especially if it's got a slight crescent shape. Through the telescope, then it's obviously inverted because it's flipped, and people get a bit, hang on, it's different. Whereas with a planet, they can't tell. Yeah, so, but it is an interesting thing. And the other thing with the finder scope, often, if you have a 90 angle on it, that flips that as well. Whereas a straight through finder tends not to.
No, it tends not to. It's the same as a binocular, usually.
So that could be confusing with it, and often more looking at terrestrial things through a finder, it's the right way up and then up.
Any other questions? Oh, you've been too easy on me. I thought I was going to have all the hard questions tonight. Okay, it's a very good question. So actually, I probably should have put that in my presentation, because for amateur getting into it, the question is always, which telescope should I buy? Which telescope is the best? There isn't a straightforward answer to that, because the best telescope is the one that you actually use. So the easiest way to answer that as somebody who's, I've been curator for, I don't know, 10 years, more than 10 years, and I was part of Astron, so I've talked to many amateurs who are just getting into telescopes who want to know what the best telescope is. And I talk to people who say, I just want the biggest, best that I can buy. Money is no object, what should I buy? So, you know, you could have an 8-inch Dob like this, or you could get a 12 or a 14 or an 18 or a 20-inch Dob. But the reality is it gets harder and harder and harder to set up. So if you're in Auckland, and so I mean, the same with if, you know, you can, you know, going for, you know, something like a Celestron Edge HD, really cool telescope on a go-to mount, that's really cool. But you're going to take it outside and it's going to take you, if you're inexperienced, an hour or two to get it set up. Even when you're experienced, it's probably going to take you half an hour to get it set up and ready to image. Whereas dragging your Dob out of the garage, particularly if you've stuck some wheels on the bottom, you're going to do that. You're going to go out and look straight away. If you haven't got a telescope at all, you're just starting out, are you? So do you have you don't have a telescope. Do you have binoculars? Buy binoculars, okay? So that is the one bit of advice that I can say in terms of what's good and what's not is have a pair of binoculars. I will plug Astrons because they have the most affordable binoculars that there are on the market, and we spent a lot of time and effort to make sure that they were suitable for astronomy and that they work. And as a person who serviced them for a decade, I can tell you there's very few come back unless they've been physically damaged by, you know, drop down the stairs or something. But have a pair of binoculars. You'll spend a little over $100, but you can always have them with you. So even once you've bought a telescope, having a pair of binoculars there gives you that ability to have a very intuitive view of the sky. When you start using a telescope, you start using a Dobsonian telescope, there's a finder scope, and that's what Nevin was just talking about. It's on there. I should have put it on. Maybe I did need the finder scope for my demo after all, Bill. You put a finder scope on there, and you'll use that to kind of, finder scope's going to give you a bigger view of the sky. When you look through the main eyepiece, you're going to see a smaller portion of that. But you want to be able to look for what you want to see. Having a pair of binoculars is about the same field of view as the finder scope on most telescopes. So you can see an interesting part of the sky. You can pick up your binoculars because it's intuitive. Maybe you want to look at the Jewel Box, which is near the Southern Cross. You can use your binoculars. You can see, hey, what does the sky look like around that area? And you can observe with that. So 50mm binoculars are still going to give you probably 70 or 80 times the amount of light into your eye than your unaided eye is. When you look at the sky through binoculars, there are so many more stars than you can see. So you think binoculars are just, yeah, that's not really going to be a serious observing tool. Super, I'd recommend everybody have a pair of binoculars and take with them. But when you look through there, you see about the same thing. Then when you go look through the eyepiece, if it's a right-angled eyepiece, as Niven said, it's going to be a weird orientation. But you'll know when you're on target because you're seeing the same thing. And then you can adjust it, get your object you're interested in right in the crosshairs, and then if you've set it up right, you'll see it in the main eyepiece. So definitely a pair of binoculars. As opposed to where do you go next? Well, as a society, this is one of our rental scopes. We have a whole bunch of these. This is one of our rental scopes. We have a bunch of equipment that's available to our members at a cost price which is really just to allow us to keep them maintained. So $10 a week, you can take home an 8-inch Dobsonian and go hard with it and have a play with it and see if it suits you. If you live in an apartment where you've got 3 flights of stairs to go down before you can observe, a Dobsonian is probably not the thing that you're going to actually go out and use. But if you've got a garage or you've got a patio or something, you can just carry it outside and plonk it down and start observing. It's going to be easy. So the answer to the question is the best telescope is for you, the one that you will use. The one that stays in the corner of the garage, however expensive it is not a great telescope. Did that answer your question?
You haven't mentioned digital telescopes.
I should have mentioned digital telescopes, shouldn't I? I should have added that as a class. And yeah. Digital telescopes are great. They are fantastic. They allow a new way of seeing the sky. So the smart telescope is usually, most of them are Newtonian designs. I suspect we'll see, I don't think any are SCTs yet. I think they're all Newtonian designs. But what they do is typically put a camera in place of the secondary mirror. They live and die on the software. So they're usually quite small apertures. So you're not really receiving a lot of light, but because it's going straight into a camera, the camera is compensating for that. So whilst you're not getting a really bright image from the telescope, if it had a physical eyepiece on, the camera is going to take 30 seconds worth of images, and it's going to stack those together to give a bright image. The part of the place that digital telescopes really fit in well is in showing you something new and making it easy to use without having to learn the sky. A few years ago, I would have stood up here and said, it actually doesn't matter what you buy, you really have to learn some astronomy before any of this, no matter how much you spend, is going to give you any results. So with most mounts, they'll have things to help you get them polar aligned, things to help you get them level, things to help you get them pointed in the right direction. The new generation of digital scopes are literally put it down, make sure it's sort of level, turn it on, connect to your phone, and then run an automated routine. What they actually do is they typically will know where they are because they've got a GPS chip in there. They'll typically know how they're orientated because there's a MEMS sensor to tell it which way it's tilted. They'll move. They've usually got a magnetometer, so they know which compass direction they're in, which gives them a kind of basis. But all of that isn't really needed because they take an image and they use software to say, where am I pointing it? It's called plate solving. Once they've done that, the telescope knows where it's pointing, and it will correct in the computer memory what angle pointing relates to what area of the sky.
So the polar alignment is automatic with some of those mounts?
So typically they're all ALTAs. So you're not really going to get super amazing astrophotography with 120 hours worth of exposure over 6 weeks. So usually they're ALTAs, and you'll get images where you're taking images and they're maybe a minute or two sort of max, and you're going to end up with field rotation in there. But they are super easy to use because the software allows you to just say, hey, I want to look at M42, and it will just point there, it'll start taking an image. They build communities, things like doing occultations and looking for interesting objects on the sky, because their software is connected to the internet. So there are communities of people saying, hey, look at this part of the sky at this time of night for something transient. And they're really good in group settings. So the reason Niven's excited about digital scopes is in group outreach. You can hold an iPad and you can say, I want to point here, and the telescope will point there, and you'll get an image of the thing that you want to look at in the sky. The compromises, though, as is everything. And in fact, my whole presentation could have been titled The Compromise of the Different Telescope Designs. Everything is a compromise. So, you are not getting a huge aperture. You are probably not getting you're not getting the best quality camera that you can get to do astrophotography. You're not getting the most stable mount, but you're getting a grab and go platform that you can literally, so the question may be, if money is unlimited these days, have a digital scope. If you are living in the third floor of an apartment block and you can't do anything else, have a digital scope that's easy. It possibly comes already in a backpack or an easy carry bag. Then you can go out to the park, turn it on. It's all rechargeable. So they are great scopes. But they're, I guess, from an amateur astronomy point of view, they are what they are. So you can't really upgrade them. You can't put a better camera on them. You can't add them on a different mount, so you can do that. But that's not to take away from them. I think they're a fantastic innovation, and I think we're going to see more and more of them. And I think what we will see in the years to come is normal mounts for standard astronomy telescopes becoming smart. There's no real reason why you couldn't have an 8 or a 12-inch Schmidt-Cassegrain telescope that is on a mount that is a smart mount that has its own ability to do the same things. And so we're going to start to see more and more of that as we go forward.
I was going to say that my one I can set up in 5 minutes.
Yeah.
And with the iPad, it's so easy because it tells me how many degrees I'm out.
and yeah, I can get done in 5 minutes. And typically, I'll do 10-second subs for anywhere between 45 minutes and 2 hours.
Yours is the C-Star, isn't it?
Yeah,
Yeah.
S50.
Yeah. So yes, that does have an equatorial mode.
And I can do, you know, look in there, those probably my photons is probably the clearest. I've got, it's a bit pixelated, especially with blind a little bit. You can definitely see the grain in this. But yeah, for me, kind of in my chair, 5 minutes, set it up, 5 minutes, pack it up, done. And I mean, you've seen some of the photos I take, and they're pretty decent. Because I come from a amateur photography background rather than astronomy, so for me it was like the best, not so much compromise, but it was the best fit for me.
And that's an important point, right? What I've found is talking to a lot of photographers are more comfortable with looking at the sky digitally. Photographers are happier with this concept that I can see something different through a camera than I can with my eye. But there's another class, it's not really a class, of astronomer who doesn't think you get a good connection with the sky to do that. You know, so there is something. I mean, I'm in the middle. I kind of think both ways are cool, right? But there is something that's kind of special about looking at a galaxy that is millions of light years away through a telescope with your eye, and just thinking about the fact that those photons of light were generated millions of years ago. They have traveled through a mass quantity of universe. They didn't get blocked by anything in between me in millions of years from that object or that galaxy in my eye. I think there's something super special about that. And you don't experience that with digital photography. But on the same token, visual astronomy is all about faint fuzzies that you've got to kind of imagine what they look like. Whereas using a camera, you can really see the spectacle of what's there. So again, the compromises, and there is no right and wrong decision. And all of these things, all of these classes of telescopes still exist because everything's a compromise and because everything is how you prefer. Anyway, I've gone over time. Is there any more final questions? If not, thank you very much.
Thank you.